Hey all, we're going to dive into the Unit 5 notes. If you would like to do the optional extra credit, here is what it looks like. You'll access the form, you'll put in your name, your block, and click yes, you agree on the first page, and then that will open up these questions. So the link to this is in Canvas under this video, and if as you go through, there is one question per slide, and these questions, answering them correctly will earn you 1 point of extra credit per correct answer. If you answer it incorrectly, you will not earn the point of extra credit. And it is important that you answer the questions correctly, that you know what the right answers to these questions are, because this is the knowledge you need to learn from Unit 5 for this class. So Unit 5 is on oceans and atmosphere, and the role of the ocean and the atmosphere in redistributing heat around Earth to make our planet a comfortable place to live. The first concept is differential heating. Different parts of Earth are heated differently by the sun on any given day. We call this differential heating. This is caused by the tilt of Earth's axis and is also why there are different seasons. It explains why the equator has a very warm climate year-round and the North and South poles have very cold climates. So as you can see here near the North Pole, the sunlight, it's the same amount of cubic sunlight, and down here it's the same amount of cubic sunlight, but this person at the equator versus this person standing in Northern Europe closer to the North Pole, they experience the same amount of sunlight in different ways. So here, all the sunlight is hitting directly on this person. And if you're standing at the equator, the sun is going to feel warmer. It's going to feel more intense. If you've ever lived or visited New York or Connecticut or a northern part of the US in the winter, if you've gone outside on a sunny day, you might have noticed that you have light from the sun, but it's like there's no heat. It's very cold. It's not you have light from the sun, but you don't really feel the same amount of heat. The sun is also located lower in the sky. But if you come down here to North Carolina, or if you keep going south towards Florida or towards the Caribbean, you'll notice that when you walk outside on a sunny day, the sun itself feels warmer. It feels more intense. And that's because of the difference in the directness or the indirectness of the sunlight as it hits Earth because of the tilt of Earth's axis. So the North Pole and the South Pole get indirect light because of the tilt. The sun is lower in the sky, it's at an indirect angle. The same cubic amount of sunlight covers a larger area. So, whereas here, so for example, here, if one cubic of sunlight hits 1 cubic of land, it's a 1-to-1 ratio. Whereas here, if 1 cubic of sunlight hits 3 cubics of land, it's actually 1/3 the intensity of the sunlight here. So that's just an example. It's not an exact of how it mathematically works out in different places, but just to help you understand that the sunlight, the reason that we have ice and snow in the North Pole and the South Pole year round for the polar bears and the penguins is because there's not enough sunlight to provide enough heat because of the indirectness of that angle because of the tilt of Earth's axis. The second concept we're covering for Unit 5 is convection. Convection or a convection cell. A convection cell is one entire cycle of heat and cold. Convection is a process that transfers or moves heat in water, air, and even molten mantle rock in our asthenosphere beneath our crust. Warm material rises because it is less dense. Cold material sinks because it is more dense. This process circulates the material itself and also redistributes the temperature to even out the temperature of all the material as a whole. So convection can happen in anything that is fluid. So it can happen in anything liquid or anything gas. It can't necessarily happen in something that's completely solid because of the rigidity of that structure. So we know that gas is less dense than liquid. Liquid is less dense than solid, or if I say in reverse, solid is more dense than liquid. Liquid is more dense than gas. And we know that because we know that air always bubbles up. If you put air in water, it will always rise up because it's less dense. If you put a rock in water, the rock is going to sink because it is more dense. So different materials have different densities, and within a given material, there can be differences in densities based on temperature. So here in this example of boiling water, we see that the heat of the gas on the stove is heating the pot, which is heating the water. That heated water, as the water heats, as it gains energy from the heat, the particles in the water actually expand or move apart and make themselves less dense. Because they are less dense, they then rise up through the water and form those bubbles that you see in boiling water. You see some of it gains enough energy to change state completely and go from being liquid to gas. So you see the steam and evaporation that comes off of that boiling water. Um, but the water that is heated but doesn't evaporate it just rises. And then as it gets to the top of the water, because of the evaporation, because it's cool above the water in our room temperature houses, that water then cools, and as it cools, it becomes more dense. As it cools, it loses energy, and the particles become closer together, so they're more dense. And because they're more dense, they then sink. Where they're exposed to the heat again, that heated material then rises and continues that convection cycle or that convection cell. So heated material rises, cool material sinks. This happens in water and this happens in air. You can see warm air rises, cold air sinks because of the differences in density that are associated with that. So convection is that process in which warm material, warm air, warm water rises, cold air, cold water sinks. And that also happens in our asthenosphere and our mantle, and that was what drove plate tectonics, or the different kinds of plate boundaries and the movement of our crust. Is the molten rock that actually goes through mantle convection as well. Our third concept is the thermohaline ocean currents. So we have global ocean currents that redistribute nutrients, they redistribute heat, they redistribute salt even, and oxygen, and they act as channels that help animals like whales and porpoises migrate throughout our planet. So they help these things, but what causes these ocean currents? What causes these currents? And what do we need to know about them, and how do they relate to climate and to the temperature of our planet? So ocean currents play a very important role. They redistribute heat from the equator and cold from the poles, from the North and the South Pole. These currents are caused by differences in temperature and density. So at the equator, the water is warmed up. As it's warmed up, it rises. And then because of different wind patterns, it blows across the surface of the earth and carries that warm water, which then warms the air above it and affects local regional climates. Eventually, that warm water will make its way towards the North Pole or towards the South Pole, where it will cool and sink. It doesn't simply sink because it grows cold, but in the poles, you see the development of something called sea ice. So we know there's a lot of snow and ice at the North Pole where the polar bears live, and there's also a lot of snow and ice at the South Pole where the penguins live. So as that ice forms, as the water freezes, most of the water freezes and forms those freshwater glaciers or the freshwater sea ice. There might be traces of salt, but it's mostly frozen, just frozen water. And some of that salt is left behind in the ocean. So the ocean itself becomes saltier. So not only is the water becoming really, really cold because of the ice, because of the cold temperatures, because of the indirect sunlight, but then it also becomes extremely salty. And both of those make the water extra dense because it's really, really cold and it's really, really salty. That water becomes so dense that it just sinks and drops to the bottom of the ocean. And then it travels around the world. So that cold current then travels around and carries with it this salt. It carries with it the dissolved oxygen. It carries with it the cold temperatures. And those cold temperatures are then cooling other parts of the earth as well. So just like the warm temperatures from the equator warm different parts of the earth, the cold temperatures from the cold are then recirculated from the North Pole to other parts of the earth. So as we see those transitions, we know that it's important for our planet to not be too hot and not be too cold, to have our ocean, to have our liquid water that redistributes that heat for us so that every place on Earth can support life. Our fourth concept is the specific heat capacity of land versus the specific heat capacity of water and what that means. So, water has a high specific heat capacity. So, it takes longer to heat up and it holds heat longer. Land has a low specific heat capacity. It heats up quickly and loses heat quickly. This is one reason why coastal areas have moderate climates compared to far inland areas. So, if you've ever been to the beach, if you've ever been to Myrtle Beach or Wilmington or some other coastal area, you may have noticed that the temperature is different. The weather is different at the beach versus farther inland towards the mountains or towards the middle of our country. If you're at the coast, you have this giant body of water called the ocean that helps regulate its temperature. So, in the winter, it might be 50 or 60 degrees at the beach, but if you go farther inland to Charlotte or to Asheville, it could be 40 or 30 degrees on that same day. In the summer, it might be 70 or 80 degrees at the beach, but if you go farther inland to Charlotte or Asheville, it might actually be 90 or 100 degrees. So the temperatures are different because of the different heat capacities of land versus water. So what happens is if you compare it to a stove, land is like the stove top, and then the ocean would be like our pot of boiling water to make pasta. So if we're going to cook spaghetti, we first have to turn on the stove. When you turn on the stove to high heat, it turns red and it gets hot very, very quickly. You know, when you see a red stove or a stove with the red light on saying hot surface, you know not to touch it, because if you touch it, it's going to burn and it's going to hurt really bad because of the heat. So land or solid or sand, soil, rock, hard surfaces, they heat up really, really quickly. Fortunately, they also cool down quickly. So if I were to turn that stove on, if I realize, oh, wait, I forgot something in my car, I need to go get that, I can turn the stove off, go to my car, come back, and then if I notice that the hot surface light has turned off, I know it's safe to then touch my stove, even though it's only been a minute or two since I've turned it off, because it has had time to return to room temperature. So land or stove surfaces or metal or solids, they heat up quickly and they cool down quickly. A classic example of this would be a cement, a sidewalk, or pavement. Water, on the other hand, has a different heat capacity. So land actually has a low specific heat capacity. It heats up quickly, it cools down quickly, and it cannot hold heat to save its life. If you heat something up that's solid, it will heat up quickly and it will get very hot, but it won't hold that heat. It cools down very quickly. Water is very different. Water is actually the opposite. It has a high specific heat capacity. That means that it takes time for water to heat up. It takes longer for water to heat up. But once water is heated, it holds that heat longer. So when we lost power during Hurricane Zeta, our electricity was dead as of like 8:45 a.m. in the morning. But later that afternoon, I turned on the water in the bathroom to wash my hands, and it was still warm. So at 1 o'clock later, hours later, the water was still warm because water holds its heat. So the electricity was off. So there was no way to make more warm water, but the water that was already hot, the water that was already warmed by our water heater, was still warm even a few hours later because water holds its heat. It has that high specific heat capacity. And that's why the climate in coastal areas is more moderate, because that water holds heat. It takes longer to heat up and it holds heat longer over time. So when you compare the different heat capacities, water heats up slowly and cools down slowly and holds heat longer. Land heats up quickly, cools down quickly, and does not hold heat well at all. And this is all important because of our next concept, land breezes and sea breezes. So because the land heats up quickly during the day, the land heats up quickly, and because the land is hot, it actually heats the air above the land. So that hot sand at the beach heats up the air above it. That warm air, because it's heated, it's less dense, like we were talking about in convection, so it rises. And that actually creates what we call a low pressure system. So as that hot air rises, over land, that happens in the daytime. Also during the daytime, if you go over the ocean does not heat up quickly. It's still cold from the night. So the air over the ocean is cooler because the ocean's cooler. So that cold air is more dense, it sinks, and then that high pressure of the cold air sinking wants to fill in the space of the warm air that's rising because it's less dense. So the high pressure, more dense, cool air is sinking in and coming towards the land from the sea. So in a sea breeze happens during the day when warm air over the land rises and cool air over the sea sinks, causing wind to blow from sea to land and creating that cycle or that convection process. And that happens during the daytime in coastal areas. At night, you have a land breeze. So a land breeze happens at night when warm air over the ocean, because it held the heat that it gained during the day, rises, and cool air over the land, because it lost everything as soon as the sun went down, it got cold. Cool air over the land sinks, causing the wind to blow from land to sea. So a land breeze happens at night. It is the cold, sinking air from the land, the high pressure from the land to the warm air, low pressure where it's rising, cool air sinking, warm air rising. That convection cell creates a land breeze at night, but it's a sea breeze during the day. And it's because of the different heat capacities of water versus land. Our next concept is the El Nino, and I want to make time to watch this video that explains it a little bit better than I do. So El Nino is when trade winds weaken and warmer ocean surface water is moved towards South America. And that has an impact on the jet stream and weather that we experience here in the US. La Nina is when the trade winds are stronger than normal and warm ocean water moves towards Asia, which allows upwelling of that cold water to be brought to the surface near South America. And again, whatever temperature the ocean is, whether it's warm or cold, that affects the air over it and affects the pattern. So when that cold water comes up, it also affects the jet stream and affects the weather we experience here in North America. So that's what you need to know about El Nino and La Nina. All right, so the Coriolis effect is the next concept, and let's watch this video. About the Coriolis effect, hurricanes in the northern hemisphere rotate counterclockwise because of that Coriolis effect, because you travel faster at the equator and slower towards the poles. But in the southern hemisphere, it is counterclockwise, the opposite. And then we have global winds. So there are three main winds that you need to know. The polar easterlies, these happen close to the North and South Pole. These polar easterlies move from east to west. You also have prevailing westerlies. Prevailing westerlies are in the mid-latitudes, so where we are in the US, but also they also exist in the southern hemisphere as well. The prevailing westerlies travel from west to east. This is why weather in the US moves from west to east. So if we know that there's rain in Tennessee, there's probably going to be rain in North Carolina because weather moves west to east in our latitude. And then farther south of us, you have the trade winds. The trade winds move east to west. And the direction is the same for the north and the southern hemisphere. So the trade winds still move east to west in the southern hemisphere. The prevailing westerlies still move west to east, and the polar easterlies still move east to west in the southern hemisphere as it is here in the northern hemisphere. And here's a video explaining more. And then what you did your sortable on the other day were the layers of the atmosphere. So our layers of the atmosphere in order. So we have Earth here where we are. The first lowest layer of the atmosphere is the troposphere. The troposphere is where we live. This is also where weather occurs. You find clouds in the troposphere. You find hot air balloons, mountains. We live in the troposphere. Above the troposphere, if you see the dotted line, above the troposphere is the stratosphere. When you fly in a plane, you don't want to get caught in a storm and you don't want to stay in a cloud if you can help it. So most long commercial flights and certainly military mission planes or spy drones fly in the stratosphere so that they can avoid the wind and the weather that occurs in the troposphere. So in the stratosphere, you also have what's called the ozone layer, which is very, very important for Earth. We'll get into that more in a minute. And then this is also where we can sometimes send weather balloons to determine what is the atmospheric pressure, what are the things that are likely to happen. As they go through the troposphere into the stratosphere, they can tell us some important information. Above the stratosphere is the mesosphere. In the mesosphere, that's where meteorites burn up. And then above the mesosphere, we have the thermosphere. The thermosphere is the layer of the atmosphere that contains satellites. It contains the aurora that occurs when our magnetosphere deflects solar radiation, harmful high energy like gamma solar radiation. And the thermosphere is the layer of the atmosphere oh my gosh, I will need to edit that part out. So we have the thermosphere above. The thermosphere is where we have our auroras. It's where we have the space station. It's where we have the satellites that orbit Earth. And beyond the thermosphere, we have the exosphere. The exosphere isn't much of a layer of the atmosphere. It's just the transition zone between our atmosphere and outer space. Beyond the exosphere is just outer space. There are not air particles. Once you start getting into the mesosphere and thermosphere, the air is actually too thin to breathe. That's why astronauts outside of the space station in the thermosphere have to wear their spacesuits and helmets, because there's no air, the air is not dense enough to breathe in the thermosphere, and it's also extremely hot and extremely cold. So to protect themselves from those temperatures and other radiation, they have to wear those spacesuits. You'll notice this graph over here. I just want to briefly touch on it. So in the troposphere, as altitude increases, so how high you are above Earth, as you go up in the troposphere, the temperature actually gets colder. In the stratosphere, because of the ozone layer, we actually see the opposite. The temperature gets hotter as you go up. And then in the mesosphere, we see the usual trend again. As you go up, it gets colder. And then the thermosphere, it gets warmer a little bit. And then in parts, it can be extremely hot because of the direct contact with solar radiation. But particles are also too far apart to conduct heat easily once you get beyond the thermosphere. So it's worth keeping in mind that how to read a graph. So here it's decreasing, or it's an inverse relationship. As altitude increases, temperature decreases in the mesosphere and in the troposphere. But in the stratosphere and the thermosphere, as altitude increases, it's a correlation, or they're moving together. As altitude increases, temperature also increases in the stratosphere and in the thermosphere. So the stratosphere, as I mentioned before, is where planes fly. Mesosphere is where meteors burn up. The thermosphere is where auroras occur and the International Space Station is located. Beyond the thermosphere is the exosphere, and then outer space. The ozone layer and CFCs. Let's watch this video real quick about what we need to know about the ozone hole. So what's cool about this story is that you hear a lot about carbon dioxide, and you hear a lot about carbon footprints, and you hear a lot about climate change and ways that humans are changing the climate on the planet, and ways that humans are creating problems. But this story is a really cool story about a problem that humans have actually been able to fix. So we noticed, scientists observed, that the chlorofluorocarbons that we were putting in our refrigerants and aerosols like hairsprays and spray paints, these chemicals were destroying ozone, and specifically, most of the damage was happening above Antarctica, but the hole was growing. So it was possible that we could destroy the entire ozone layer on our planet if we didn't do something. But the world came together. They passed they passed international efforts and laws in individual countries to ban the chemicals that were causing this problem. And over time, since then, since they've enacted that ban on chlorofluorocarbons, we've actually seen the ozone begin to heal itself. So our planet is very good at balancing itself out and taking care of itself. If we can do our part of identifying the problems we're causing and fixing them before it gets too late. The ozone layer protects us from that harmful UV radiation. It doesn't do anything for lower frequencies or higher frequencies. It only targets ultraviolet frequency radiation. Obviously, we still have sunlight come in. It doesn't block sunlight that we see, visible light, but it does target that ultraviolet. And within the ultraviolet light, there is UVA, which still comes down to Earth. This is why some people really want to make sure that all people to avoid skin cancer should make sure that they wear some kind of sun protection when you're outside a lot, whether that's sunscreen, whether that's a hat or long sleeves. Different people have different kind of natural resistance to things like sunburn, but anyone can get skin cancer from excessive exposure to ultraviolet radiation, which can harm your DNA in your skin and cause it to reproduce and form cancer. But even more harmful than UVA is UVB and UVC. These sorts of things could cause more extreme variations of burn and cancer if they're exposed to us, and that's what the ozone layer blocks and keeps us safe from. So we like our ozone layer because it protects us. The ozone layer itself, ozone is as a gas chemical is actually toxic. So when we produce ozone as smog in our cities at ground level, it's actually a bad thing there because it makes it's a poison to breathe, but no one lives up in the stratosphere, so it's okay that we have this toxic gas in the stratosphere because the properties of ozone are what block that ultraviolet light that actually protects us here on Earth. So we like our ozone to stay in the ozone layer because that's where it does the most good for us. So that's everything pretty much that you should know for Unit 5. You should have a lot of the information you need to answer these questions. If there are things you still don't understand, you can use Google while you're answering these questions. But these questions are not on the internet anywhere. I made these myself. But if you have any questions, let me know. When you submit your answers, you'll be able to check your answers and see which ones you got right, how many points you got for extra credit, and make sure you turn this in. As always, if you have any questions, let me know. But have a great day, and I will see you in class.